Hi. In the last video we have discussed about nonlinear dynamical system, and we have also introduced what is nonlinear differential equation to represent the nonlinear dynamical system. Okay. Now, in order to understand how the state variables are evolving as a function of time, we need to solve those nonlinear differential equation. Okay. But the method we are going to use to solve that nonlinear differential equation is graphical approach. So one is graphical approach. What are the other approaches available to solve the differential equation? The other approaches are analytical method. Okay, so the methods which you have learned in the course of differential equation. So those methods are analytical method. In that course you have learned certain techniques, but you cannot use those techniques because you have learned it only for linear differential equation. One of the main technique you use is a superposition principle, and that superposition principle will not be applicable for nonlinear differential equation. So for most of the cases it is very difficult to solve by analytical approach. Okay, so what else? We have another approach called numerical method. Okay, in numerical method, the things which we have learned in computational methods, the techniques we have learned in that course, and we will solve that differential equation, and that will give an approximate solution of x, the state variable, as a function of t. But it is okay for a very short range of solution. For example, if t goes from 0 to, let's say, 10 or 100, you can use that approach. But for example, if you want to know what if t goes to infinity, okay, then that method fail. Okay, so therefore for certain cases the graphical approach is an advantageous an approach compared to other two approaches. Okay, so what is this graphical approach? In order to understand what is this graphical approach, we'll see one example. Okay, before looking at the graphical approach, we'll see the advantage in the graphical approach. Okay, let's look at this equation, which is okay, let me slightly increase the size. Okay, so this is the differential equation. X dot is equal to sine of x. Okay, and for this differential equation I want to know what is x as a function of t. Okay, so what we are going to do is, in the place of x we are going to put dx by dt, so that I could rearrange that in this manner. Okay, and then if I integrate at both sides, I will get t at this side, and the integration, which will provide me this solution. Okay, where c is based on the initial condition. The initial condition, let's say x is equal to x naught at t is equal to t naught. So if I impose that condition, I'll get c is equal to ln of cosecant x naught plus cot x naught. Okay, norm of. Okay, then finally if I put that c, whatever I have obtained over here to over here, I will get t is equal to this expression. So what we need is x as a function of t, but anyway we have got a relation between t and x. Okay, here I have used an analytical approach. Okay, fine. Now with this relation I have solved it completely. This is an exact solution. Okay, now let's say for such a system I have some questions, and let's see whether this solution is able to answer those questions. So the first question is, if the initial condition x naught is equal to pi by 4, okay, how x is going to vary as time increases from 0. Okay, so that's one question. And what is the value of x? Will x approach some finite value as t tends to infinity? So that's a question. Okay, so if you see, if I give x and if I ask what is t for that particular x, I could identify what is that time. Okay, but here they have asked an inverse result, relation, right? So how can I solve this one, as particularly this one? Okay, if t goes to infinity, what will happen to x? Okay, so in order to identify, what we are going to do is we are going to plot this equation. Okay, so if I plot this equation, to plot this equation I am going to use Desmos. Okay, it's an online graph plotter. So where this axis is t, but here I should express that as a x, and this axis is x, which I express as y. Okay, and if I but this is the curve which I will get. Okay, and the initial condition a, okay, I have mentioned that as a, which is pi by 4 I have given. Okay, so what is this pi by 4? Where is this pi by 4? It is at this point. Okay, so the pi by 4 is at this point. Okay, as time which is this one, if time approaches infinity, which means very large, it's not keep on increasing, but it seems like it's approaching to a finite value, isn't it? So I do not know what value it's approaching, but some finite value. Let's say, what is that finite value it's approaching? It's slightly above 3, maybe I'm just guessing, maybe it's pi. The answer is maybe it's pi, y equal to pi, let's say. Yes, so if we see, this is y equal to pi line, and it's approaching this asymptotically. This line is approaching this line. Okay, so I could somehow answer this question. Okay, but in order to answer this question, I have to go through all these steps, right? I have to remember how to do the integration of these things, right? And finally I have got the answer. So the x goes to pi as t goes to infinity. Okay, what about the other question? The other question is, in the first question we have solved for when x naught is equal to pi by 4, but what if it's not just pi by 4, some arbitrary initial condition, and at that time what will be the fate of x as t goes to infinity? Okay, let's see whether we are getting the same solution if I change a, which is the initial condition, right? So instead of pi by 4, let me put pi by, I don't know, why don't I put pi by 6? Okay, so yeah, it seems like even for pi by 6 it's approaching the same value. Okay, why don't I put 0? Okay, if I put 0, okay, if I put 0, there is a problem because this value goes to infinite. Okay, so that's a problem. So let's not use 0, let's use just pi, or let's use minus pi by 4. Okay, minus pi by 4. Okay, where is minus pi by 4? Okay, this line. Okay, that's some initial point or the initial value, and as time goes on it's going to a different value. Okay, so it's going to a different value, and that value is something like minus pi. Okay, that value is minus pi. Okay, so so what I could understand is it depends, the final value approaches to a certain value, sorry, the value of x approaches to a certain value as t goes to infinity, which depends on the initial condition. Okay, so I can't give a general picture. Okay, all I have to do is I have to use different initial condition. For example, let's say if I put in the place of just pi by 4, say I don't know, maybe 3 pi by 4. What if I put 3 pi by 4? Is it okay? That's 3 pi by 4. Even if it's 3 pi by 4, the solution is approaching to pi. What if it's 5 pi by 4? So this is 5 pi by 4, and the solution is still approaching pi. Okay, it seems like if the initial condition is positive, then my solution is approaching pi. If the initial condition is negative, my solution is approaching to minus pi. Can I conclude like that? Okay, why don't I put 7 pi by 4? Okay, so this is 7 pi by 4, and still it's approaching. Okay, it seems like our conclusion looks right. Okay, I don't know, maybe 10 pi by 4. Where is that 10 pi by 4? Ah, yeah, 10 pi by 4, it's here. Okay, but now it's approaching to a different value. It's approaching to a different value, which is, I don't know, what is it? It's approaching near to 9. Is it something like, yeah, it's 3 pi. Interesting. Okay, so basically what I have understood is the final value of x depends on the initial condition. Okay, but this equation looks very complex, and I couldn't understand this equation. Okay, so in order to understand the equation in a better manner, we are going to look this problem in a totally different perspective. Okay, we're going to look this problem totally in a different perspective, and that is the geometrical way of thinking. Fine. So we'll see what is that geometrical way of thinking in the next video.